Have you ever calibrated a rainfall runoff model that still produced hydrographs that were too flashy, peaks that arrived too early, or recession limbs that dropped too quickly? In many cases, the issue is not your routing method, your losses, or even your rainfall data. The missing process is surface depressional storage, the countless depressions, wetlands, ponds, and micro-topographic features that temporarily store water across the landscape and fundamentally control catchment response. Today we will break down why surface depressional storage matters, why it is so often neglected in hydrologic modeling, and how we can quantify and incorporate it into our models. Stay with me. When we think about storage in hydrology, we usually focus on major reservoirs, channels, or detention basins. But across real catchments, there are thousands of much smaller storage elements such as surface depressions, ponds, wetlands, and micro-topographic roughness. Individually, they may seem insignificant, but collectively, they can capture a substantial portion of rainfall and strongly influence runoff generation and routing. Surface depressional storage can be found in different forms. First, surface depression, which are closed topographic lows that trap water until their storage capacity is exceeded. These features influence runoff through several mechanisms, including abstraction before overland flow begins, peak attenuation, delayed hydrograph response, enhanced infiltration under ponded conditions, and evaporation losses after the event. In depression-dominated watersheds, time to peak can increase significantly, while peak flows may reduce by 10 to 40% for moderate storm events. Next are ponds and wetlands. Small ponds and wetlands provide more persistent storage. This includes farm ponds, ephemeral wetlands, riparian wetlands, and forested wetlands. These systems store water and also regulate flow gradually through infiltration, seepage, and evapotranspiration. They also provide important co-benefits such as sediment trapping, nutrient processing, groundwater recharge, and base flow support. Finally, micro-topographic storage. This includes tillage roughness, vegetation clumps, hummocks, and forest floor storage. These features may only store a few millimeters of water, but they delay runoff initiation and increase infiltration opportunity time, especially during the smaller and more frequent storm events. Despite its importance, depression storage is commonly ignored in rainfall runoff modeling. Let's explore why. One major reason is data limitation. Traditional DEMs with 10 to 30 meter resolution simply cannot resolve many small depressions or micro-topographic features. In some cases, they miss the majority of actual storage. High-resolution LiDAR data provides much better representation, but coverage, processing requirements, and cost can still be barriers. Another issue is modeling complexity. Representing thousands of small storage elements increases computational cost, parameters requirement, and calibration uncertainty. When surface depression storage is ignored, several systematic biases commonly emerge. Hydrographs becomes excessively flashy, peaks are overestimated, lag times are underestimated, recession limbs become too steep, and runoff volumes are overpredicted. Models may also generate runoff for small events that produce little or no observed flow in reality, because the storage thresholds are not represented properly. And most importantly, model calibration suffers. Neglecting depression storage during calibration can result in parameter compensation, event-dependent parameters, transferability loss, and prediction errors under land use or climate change scenarios. So, how can we quantify depression storage? The first step is usually DEM analysis. High-resolution LiDAR data, ideally 1 to 5 meter resolutions, allows depression identification and storage volume estimation. From this, we can derive key metrics such as maximum storage depth, depression density in the catchment, size and spatial distribution, and connectivity. Remote sensing can also help identify wetlands and seasonally inundated areas using aerial imagery or satellite data. And finally, field verification wherever needed. This can include surveying the depression geometry and measuring infiltration rate and other soil properties. Once quantified, storage can be implemented in our models. Depending on the model type, the implementation method may vary. Let's know more about it. In conceptual lumped models, the simplest approach is to add storage as an additional initial abstraction. Note that in this approach, storage is treated as a loss, not a routing element. Therefore, there is no temporal redistribution. In a more realistic approach, you can explicitly represent storage as a routing component using conceptual reservoirs with defined storage volume, stage storage curve, and an outlet structure such as a weir with a crest at maximum storage elevation. In distributed models, on the other hand, you can implement natural storage at a grid-based level or as explicit depression objects. Finally, in 2D hydraulic models, natural storage can be represented directly if a high-resolution DEM is used as terrain. Also note that the grid resolution must be fine enough to resolve depressions. It is also needed to enable infiltration in the 2D cells. It is worth noting that in many practical applications, a simplified lumped storage approach already captures most of the benefit without excessive complexity. Practical recommendations are as follows. First, start with your initial results. If observed hydrographs show a gradual rise and fall, but the initial model produces a flashy response, storage is likely the cause of the discrepancy. Second, perform a preliminary depression analysis if high-resolution DEM data is available. If watershed average storage exceeds roughly 2 to 3 mm, depression storage should be seriously considered in the model structure. You may be able to ignore such storage in steep terrain where depressions are rare and can drain rapidly. Third, don't ignore temporal variability. Storage capacity can change over time due to vegetation growth and sedimentation. You may need to revisit the storage capacities once new data is available. Fourth, avoid unconstrained calibration of storage parameters. Storage estimates should primarily come from DEM analysis and field evidence, not purely calibration. Fifth, avoid excessive model complexity. Representing every individual depression may not necessarily enhance model performance. And finally, validate storage behavior physically, not just statistically. Don't only look at 1 or 2 performance metrics. Also evaluate the hydrograph flashiness, recession behavior, and lag times. As we discussed, in many cases, even a relatively simple storage representation can dramatically improve both model realism and predictive capability. Because ultimately, good hydrologic modeling is about representing the dominant physical processes controlling how a catchment behaves. I hope you have enjoyed this video. If so, please share it with others and stay tuned for more videos like this. Thank you for watching. See you in the next one.